Troy Weckenbrock, and these are my two teammates, Nicole Ricker and Aaron George, and together we make up Team F. The project this semester was to design and build an advanced energy vehicle that could travel around the Jurassic Park island. The subset goals of this project were to design an efficient vehicle that could travel around the island, getting through two gates, an entrance and an exit gate, picking up a caboose filled with baby dinosaurs and visitors, as well as making it all the way back to the visitor center.
For this project, there were time and design constraints. The team had to come up with a working AEV by the end of the semester. This was a huge time constraint. Another time constraint included the time it took the AEV to travel around the track. The maximum time allowed for the AEV to complete the run was 2.5 minutes. Design constraints included making sure the Arduino board was at least 2 inches away from the magnet that picked up the caboose and making a design that hung below the track.
This video will show the progression of the AEV through the design process, starting with the initial designs and ending with the final design. The team had a test on the track during lab periods. The testing included writing a code, doing performance analysis tests, and trying different designs to determine which one gave the best efficiency.
The team initially came up with 3 designs. These designs were brainstormed after the first lab period where the team built a sample automated energy vehicle. This sample AEV allowed the team to decide how to design their own AEVs. All 3 designs were small, compact, aerodynamic, and used 3D printed parts to increase aerodynamics while not adding a lot of weight. The overall goal of the team's design was to make the AEV as small as possible to minimize the weight.
After each team member came up with their own design, the team performed concept screening and scoring analyses to determine which design or combination of designs to continue with. This then gave the team ideas of which design should be tested next. When looking at the concept screening and scoring sheets, the team determined that they should continue with a combination of all 3 designs by making a small, compact AEV with a cooler configuration. This new design was tested in lab, and it was determined that the team should also test a pusher configuration in order to determine which configuration works better for the given scenario.
After testing both the puller and pusher configuration designs, the team noticed that the pusher configuration was more efficient going to the caboose and after getting the caboose. The team decided to try putting motors on both sides of the AEV. This design allowed for a pusher configuration when going to the storage facility and when bringing the caboose back to the visitor center. This design also allowed for the team to use only one motor, which made the AEV more efficient. The team decided to use one propeller on either side of the AEV instead of using a servo to switch the direction of the propellers in order to maximize efficiency. Using a servo would cause the efficiency to decrease at the times when the servo direction was changed. The servo would also add more weight to the AEV. The team's final design was small and compact. This design weighed 245 grams and used low power settings in the code to traverse the track.
During the final testing of the design, the AEV used around 40% power at all times on the track. The AEV was using the pusher configuration going both ways around the track. When completing the performance analysis on the AEV, the efficiency was constantly around 11.75%, with spikes in efficiency when the AEV was braking. In the final code of the AEV, the team utilized reversing of the motors and coasting.
While coming up with a final design and code, the team faced multiple obstacles. One obstacle faced had to do with the use of coasting. Because the team used coasting, the AEV was less accurate during each run. The team overcame this obstacle by doing trial and error runs on the track. This testing allowed the team to determine what the mark count should be around when the AEV starts coasting. Another obstacle dealt with the external sensors. During almost 2 lab periods, the external sensors were not working. This was due to the sensors going bad. The team spent the class period thinking the AEV wasn't stopping because of errors in the code. After performing an external sensor test, it was determined that the sensor wasn't gathering information and the new sensor had to be obtained.
At this project, the team was able to successfully design an AEV and write a code that brought the AEV around a track to transport baby dinosaurs. The team learned about how working designs are changed and updated based on tests performed. The team also learned how to work in a team environment and how to create engineering documents, including executive summaries, a project schedule, and a project notebook. The team would like to thank everyone who helped throughout the design process, including Professor Savridis, GTA Carlos, the UTAs, and EEIC.